All right, so this video lesson is a part of our look at forces is going to look at Newton's second law of motion as well as the difference between weight versus mass. So getting into this, Newton's second law of motion, it's the relationship that we see between the net force that's acting on an object, the mass of that object, and the acceleration that it experiences. And what we see here is that the relationship is linear. So as the net force on an object increases, the acceleration will increase at the same rate. So if you double the force, you double the acceleration. If your acceleration is measured to be 4 times greater than what it was with a different force, that means that the net force was 4 times higher acting on it. And that's what we see, right? The acceleration is directly proportional to the net force and inversely proportional to the mass. So think of it this way. If you push on a shopping cart and then you increase the mass of that shopping cart by putting various food items in it, and you still push with the same amount of net force on it, your acceleration is going to be less because your mass went up. That's really what we see in terms of that inversely proportional to mass. Again, why larger objects are harder to accelerate. Because if a small car applies the same force as a large truck, the large truck is more massive. If the same net force is acting on them, the smaller vehicle will accelerate at a faster rate, thus reaching top speed faster. Also, if you want to slow the object down, it's the same thing. If the same net force is acting on a heavy truck compared to a small car, the small car will experience a greater acceleration, so it will slow down it's going to slow down and stop faster. So remember, net force, right? Combining all those forces, you can only look in that given dimension. Remember, vertical forces you can combine, horizontal forces you can combine. You can't go between the two dimensions. So our net force is what causes this. If there's only one force given to you, that's going to be your net force. If you start seeing, hey, we've got friction and an applied force and tension and you start seeing different forces that are acting on it, then you may need to turn to a free body diagram to help you determine the net force. If you're given mass and acceleration, you do not need to turn to a free body diagram. Instead, you can come to Newton's second law of motion here to determine what the net force is acting on an object. So a quick check on concepts here, just to get an idea of proportional and the inverse proportionals that we see. Object A has a mass of 20 kilograms. Object B has a mass of 40 kilograms. There are 4 questions on this slide here. What I want you to do is quick pause the video, make some predictions, and then unpause it and hear what the answers are. Okay, so you've had a chance to look at these questions. So let's roll through them here. So the first one, to accelerate them both at the same rate, how will the force on A be, or how will the force on A be compared to B? So if we think about what we have here, if we look at F equals ma, right? That's ultimately what we have here. They accelerate at the same rate. So let's be simple and let's say that the acceleration rate is 1 meter per second per second. So for our 20 kilogram, so we're going to break this down. We've got 20 kilograms versus our 40 kilogram. Now our 20 kilogram will be F equals mass times acceleration of 1 meter per second squared. So the net force that would be acting here would be 20 newtons. On our 40 kilogram, F equals mass, which is 40 kilograms. They're accelerating at the same rate, so 1 meter per second squared. So our net force here would be 40 newtons. So we could say that the force on A is half that of B, or we could say the force on B is double the force on A. Next one that we're going to look at, if they both undergo the same force, how does the acceleration on A compare to B? So now we're looking at the exact same force. We're still going to stick with our 2 columns here, but now we undergo the same force. So let's say that they each undergo a force of 80 newtons. So we'll go 80 newtons equals our mass times our acceleration. And that's going to be the same for each. So 80 newtons equals our mass, which is 40 kilograms for object B, times our acceleration. Dividing these out, we're going to get that the acceleration of our 20 kilogram object is 4 meters per second squared, and for our 40 kilogram object is 2 meters per second squared. So the acceleration on object A is going to be double that of the acceleration of object B because it has half the mass. Looking at our third scenario here, how much force is needed to accelerate object A at a rate of 2.5 meters per second per second? So here we're looking at object A, so the 20 kilograms. So F equals our mass of 20 kilograms times our acceleration of 2.5 meters per second squared. And this is going to get us a net force of 50 newtons, is what that's going to give us here for the third one. Again, just a base F equals ma is what we're going to do there. For our last one, if you apply 25 newtons of force, how fast will object B accelerate? So we'll go with a different color here for the last one. So you are now applying 25 newtons of force, and that is going to be equivalent to our mass times our acceleration. So we can divide this out, and the result that we're going to get is 0.625 meters per second squared is where we're going to be at on our concepts here, right? So here we have two concepts for the first two bullets, and we have two quick calculations for the last two. Now, another one to look at, and again, try this on your own before clicking through or before allowing this to play through to see the solutions. So this awesome blue car right here, the Shelby Supercar Ultimate Aero TT, can go from 0 to 60 miles per hour, which in metric is 0 to 26.8 meters per second in 2.78 seconds. It has a mass of 1,247 kilograms. What is the net force on the car as it runs the 0 to 60 test? Attempt this problem first, and then allow the video to continue playing to see what the solution is. Okay, welcome back. Here's the way that we would approach this problem. First, looking at F equals ma, you will go, hey, I know the mass. I'm looking for the net force. So what's my acceleration? What do I know for acceleration? For this, you can go back to the definition of acceleration, which is your change in velocity over your change in time. If you thought that the formulas from one- and two-dimensional kinematic motion went away, I'm sorry, you are mistaken. We are still going to be able to apply those formulas from one-dimensional and two-dimensional kinematics to help us find accelerations of objects through this unit. So we go with our change in velocity over our change in time. So final velocity 26.8 minus initial velocity of 0 divided by our time of 2.78 seconds to get our rate of acceleration of 9.64 meters per second squared. Then we can use that acceleration, multiply that by the mass of the vehicle to get the total amount of net force acting on the vehicle. Key thing here is this is the net force. This is not the force that is being applied by the vehicle's engine, right, or by any forces that are allowing the object, the vehicle in this case, to be moved forward. This is the net force. This is the overall force. Remember, there will be forces acting against the vehicle. So the vehicle's force that it applies overall is going to be greater than this 12,000 newtons because it has negative forces working against its motion. Next idea here, and it does pertain directly to Newton's second law of motion, is the difference between mass and weight. Mass, going back to chemistry, right? It's the amount of matter that an object has. It's how much stuff makes up an object. And your mass doesn't change depending on where you are, right? So your mass is your mass. You go to school. Your mass is the same as when you're in your vehicle, which is the same as when you are on an elevator, which is the same as when you are on a roller coaster, right? Your mass is going to stay the same. We measure that mass in kilograms, right? Because mass, the base unit of mass is grams in the SI system. In physics, we use kilograms. as the base unit here. So everything in physics is based on the kilogram, not on the gram. So make sure everything is converted into kilograms. That's mass, right? The amount of matter, how much stuff an object contains. Weight, on the other hand, as we've previously discussed with types of forces, weight is the force of gravity pulling on an object, right? Pulling that object towards the planet. This then becomes dependent on the rate of acceleration that a planet is able to exert on an object, right? So what is the acceleration due to gravity on any given planet? That's what your weight depends on. This is the whole idea that when you go to the moon, you're lighter because the acceleration due to gravity on the moon is far less than it is on Earth. Or if you were to go to Jupiter, the gravitational acceleration on Jupiter is far greater than it is on Earth, which is why you would be much, 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 much heavier on Jupiter than you would be here on Earth, right? It's based on that little g, right? That negative 9.81 meters per second squared on Earth. That changes depending on where you are located. So your mass doesn't change. You go to the moon, your mass didn't change, but your weight did because of that gravitational pull. Weight is always measured in newtons in the SI system. So mass is kilograms, weight is newtons. And the formula that we can use here is going to be our weight, F sub g, being equivalent to mass times the acceleration due to gravity. And that's a really important idea here, that mass times g. G is not gravity. G is the acceleration due to gravity or the acceleration caused by gravity. Your weight is a force measured in newtons. The mass is in kilograms, and g is the acceleration due to gravity. So, a quick example problem here. The world record moose that was harvested had a mass of just over 1,000 kilograms at 1,043 kilograms. How much did it weigh? Keep in mind, what we are given is a mass. We want to know its weight, which will be in newtons. Pause the video, attempt to solve this, and then press play once you have an answer. All right, welcome back. Here's the way that we would approach this problem. So our weight, F sub g, is mass times the acceleration due to gravity. So we would take 1,043 kilograms times 9.81 meters per second squared to get us 10,200 newtons. And you may be thinking on this, hey, I thought weight pulled downward, so isn't it negative? By technicality, yes, but we never, in our day-to-day living and in our basic conversations, we never actually call weight negative, right? Weight is always just verbalized as a positive value because that's the way that we perceive it. Know that if you're solving for a net force vertically, then we care if your weight is negative. And that goes for every force. The only time that we really care if it's positive or negative is when the direction truly matters. When we start trying to find the net force acting on an object, as opposed to just what is the value of a specific force. So here, because we're just looking for the weight and we don't care about a normal force, we don't care about the net force acting on the moose, we can just call it a positive value. So this is what we have in terms of finding net forces using Newton's second law, as well as our difference between weight versus mass.